A one-way slab is a type of RCC slab that's supported by two opposite sides and is designed to primarily resist bending in one direction. One-way slabs are rectangular in shape with a thickness that varies depending on the load requirements and span of the slab. One-way slabs are different from two-way slabs because they are supported by two opposite sides only, while two-way slabs are supported on all four sides. This means that one-way slabs are designed to resist bending in one direction, while two-way slabs are designed to resist bending in both directions. The aspect ratio, that's ratio of longer span to the shorter span, shall be greater than or equal to 2 for one-way slabs, and if this ratio is less than 2, then we can call it a two-way slab. In this video, I am going to discuss how we can prepare the bar bending schedule of a one-way slab along with the overview of reinforcement used in one-way slab. Before starting with the bar bending schedule, we must know about the various types of bars used in a one-way slab. The main bars in a one-way slab are placed at the bottom of the slab to resist the tensile forces that arise due to bending. These bars are placed parallel to the direction of the shorter span since the loads are carried along the shorter span only, and the main bars are anchored into the supports at either ends. If we talk about the distribution bars, these bars are provided to take care of the secondary stresses arising in the longer span due to the effect of bending. Besides this, they also take care of the temperature stresses, creep stresses, and the shrinkage stresses. One of the key functions of these bars is to hold the main bars in position while concreting. Apart from these bars, we provide top extra bars in case the main reinforcement is provided as alternative bent-up bars to take care of the negative bending moments at both the ends. Now, let's understand how to prepare the bar bending schedule of a one-way slab with the help of an example. So, we have the given data. Length of slab is given as 6 meters. Width of slab is 3 meters. The slab is provided with 10 mm main bars with a spacing of 260 mm. The distribution bars are 8 mm in size with a spacing of 290 mm center to center. The clear cover is given as 20 mm. The overall thickness of the slab is 140 mm and the development length is assumed to be 48 D. First of all, let's do the calculation for main bars. The number of main bars is given by longer span of slab upon spacing plus 1. Longer span of slab is given as 6000 mm. Spacing of main bars is 260 mm. On substituting these values, the number of main bars will be equal to 24.07, say 25 bars. The cutting length of main bars will be equal to shorter span plus twice development length plus 1 times crank length minus bend reduction. The shorter span of slab is given as 3000 mm. Development length is equal to 48 times D, where D is the dia of main bar, which is given as 10 mm. The crank length is equal to 0.42 D, where D will be equal to slab thickness minus twice clear cover minus dia bar. Slab thickness is 140 mm, clear cover is 20 mm, and dia bar is 10 mm. So D will be equal to 90 mm. The bend direction for 45-degree bend is equal to 1 times D, and since we have provided 2 number of bends, so total bend direction will be 1 times D into 2, where D is the dia of the main bar. On substituting all these values, the cutting length of main bar will be equal to 3.98 meter. The total length of main bars will be equal to cutting length of main bar into number of main bars. Cutting length is already calculated as 3.98 and the number of main bars is 25. The total length will be 99.45 meter. Weight of main bars is calculated by using the formula D square upon 162.2 into L, where D is the dia of the main bar and L is the total length of main bars. Dia of main bar is 10 mm and the total length is calculated as 99.45. Hence, the total weight of main bars will be equal to 61.31 kg. Now, we need to do the calculation for distribution bars. The number of distribution bars will be equal to shorter span of slab upon spacing plus 1. Shorter span of slab is 3000 mm and the spacing of distribution bars is 290 mm. On substituting these values, number of distribution bars will be 11.3, say 12 bars. The cutting length of distribution bars is equal to longer span of the slab, that's Ly, plus 2 times development length. Longer span of the slab is 6000 mm and development length is 40 times D, where D is 8 mm and the total will be 6.768 meter. Total length of distribution bars will be equal to cutting length of distribution bars into number of bars. Cutting length is already calculated as 6.768 and number of bars is 12. The total will be 81.216 meter. Weight of distribution bars will be equal to d square upon 162.2 into L. D is the die of distribution bars, which is given as 8 mm, and L is the total length of distribution bars, which is calculated as 81.216. On substituting these values, the total weight of distribution bars will be equal to 32.05 kg. Now, let's do the calculation for top distribution bars. These bars are provided at top of critical length, which is given as per the drawing, and this length is usually taken as L by 4, where L is the shorter span of the slab. The number of top distribution bars is given by the formula Lx upon 4 upon spacing plus 1 into 2. Lx is the shorter span of the slab, which is given as 3000 mm, and spacing of top distribution bars is 290 mm. On substituting all these values, the number of top distribution bars is 7.17, say 8 bars. Cutting length of these bars is equal to cutting length of bottom distribution bars, which is already calculated as 6.768 meter. Total length of top distribution bars is equal to cutting length into number of bars. Cutting length is 6.768 and number of bars is 8. The total will be 54.144 meter. Weight of top distribution bars is equal to d square upon 162.2 into L. D is 8 mm and L is already calculated as 54.144 and the total will be 21.36 kg. Finally, let's do the calculation for top extra bars. The top extra bars are provided in case the main bars are provided as alternative bent up bars. The number of top extra bars is given by the formula Ly upon spacing plus 1 into 2. Ly is the longer span, which is given as 6000 mm, and the spacing of these bars is twice the spacing of main bars, that is 520 mm. On substituting these values, the number of top extra bars is 25.1, say 26 bars. The cutting length of top extra bars is given by Lx upon 4 plus development length. Lx is the shorter span of the slab, that's 3000 mm, and development length is 40 times d, where d is 8 mm. On substituting these values, cutting length will be equal to 1.13 meter. The total length of top extra bars will be equal to cutting length into number of bars. Cutting length is 1.13 meter and number of bars is calculated as 26. The total will be 29.4 meter. Weight of top extra bars is given by d square upon 162.2 into L, where d is 8 mm and L is 29.4. The total weight of top extra bars will be equal to 11.6 kg. Finally, the total weight of steel required for this slab will be weight of main bars plus weight of distribution bars plus weight of top distribution bars plus weight of top extra bars, and the total will be 126.3 kg. After adding 5% of wastage, the total weight of steel required will be 133 kg. If you want the Excel sheet along with the manual calculation PDF of this problem, you can find the link in the description box of this video. And if you want to learn the detailed bar bending schedule of all the structural members, including footings, beams, columns, slabs, and want to learn the complete estimation of a building right from PCC, footings, columns, beams, brickwork, blockwork, each and everything in a single combo course, and be in a position to do the complete estimation of a building, then you can check out the course on Advanced Quantity Surveying plus Bar Bending Schedule. The link of the course you can find in the description box of this video. Thank you.